All right, welcome to Exam 1 review for Calc 1. So if we just get started at this part 1 of question 1, it says, suppose a function has a domain of all real numbers and a removable discontinuity at x equals a, which of the following statements must be true if the function is continuous at all other input values. All right, so if we try to visualize this graphically, let's kind of define that here. It's going to look something like this with the removable discontinuity, right? So if we look at the limit for this, we can see that the limit as it approaches from the left is the same as the limit as it approaches from the right, but it is not necessarily equal to that actual point, right? Because the actual point is up here. So the choice that most resembles this is choice E. We got the limit coming from the left that's equal to the limit coming from the right, but it is not equal to that actual y value. So for part 2, it says consider a continuous function defined on this interval. The function's average rate of change is 2, and what is the difference between the value of the function at x equals 6.5 and the value of the function at x equals 10? So this is an average rate of change function, and using these y values and x values that were given, it's going to be modeled a little bit like f of 10 minus f of 6.5 over 10 minus 6.5 is going to be equal to our average rate of change, which it says is 2. So it asks for the difference between those function values, and so this is going to be what we're looking for right here. And so if we multiply this on this side, we'll get f of 10 minus f of 6.5 is equal to 2 times 10 minus 6.5, which gives us 7, which is answer C. And we're just going to skip over part 3 of this first problem. All right, so for part 4, we are supposed to identify a potential graph of f with the given information. And so this is saying we have this f derivative at a, so that's going to be like our slope, right? So I'm going to kind of draw that right here, the slope of the tangent line. And it's greater than some f of a plus delta x. So if we have this point right here, this is going to be, sorry, I'll draw it out here. It's going to be f of a plus delta x with this a plus delta x being our x point. And so basically it's saying the slope at f derivative of a is greater than the slope at a later point in the graph. And so if we take a look at all 4 of these graphs and see where the slope of a is greater than a slope at a later x point, we'll see that graph 1 is a contender, but also graph 4, because we have this negative slope at a, but then the slope is getting more negative. The negative is getting larger as we go to the right for delta x is greater than 0. And so we know that 1 and 4 are our options. Let me recircuit that. All right, so for part 5, we have to identify true statements about this piecewise function. And so since it does some kind of weird behavior around the points x equals 2, we are going to kind of look at the values around these points for all the piecewise. So if we plug in 2 for our first function up there, that's going to be 2 to the 4th minus 6, which gives us 10. And then if we take this 4x to the 3rd and look at what it does there, that's going to be 4 times 2 cubed, which gives us 32. So if we draw this graph out, kind of draw a graph here, it's going to kind of come down here and then come back up at x equals 2. and this is a point 10, right? Because we got 10 from this first piecewise, and then it equals 10 at x equals 2. And then we're going to come all the way up to 32 and kind of continue our stuff up there. And so if we look at all of these statements, we can see that f is not continuous at x equals 2, but we can see that the limit from x to the left is equal to f of 2, right? It is not differentiable at x equals 2, and the limit does not exist at that point either. So the only true statement is 2.
So for this problem, it tells us that the Earth exerts a gravitational force it gives us this function f of r. That's a gravitational force equals 2.99 times 10 to the 16th over r squared newtons, which is they're calling n, or that's the unit for it, on an object with a mass of 75 kilograms located r meters from the center of the Earth. Describe the meaning of the following expressions. Your response should identify the quantity represented by the expression. Specify the units associated with each expression. So, for this, importantly, we're just describing what the expressions are. We're not actually having to solve for this. So to describe this first one, it is f of 6,790,000 minus f of 6,770,000. Well, this f represents force, and this is a force. So we have the difference in forces at two different distances from the center of the Earth. So what this is going to represent is going to represent the, sorry for my handwriting, difference in gravitational force from the Earth, or maybe exerted from the Earth. I don't think that would make a huge difference. On an object uh, 6,790,000 meters from the center of the Earth, and 6,770,000 meters from the center of the Earth. The Earth. And then I'll say, because I need to include my units, in newtons, or just in n. Or I'll write newtons, just to make it a little bit more clear what I mean by that. But I'm pretty sure if you just put n, they'll get what it means because it tells you that. So the difference in gravitational force, because this is a force minus a different force, so the difference in the forces from the Earth on an object, that's just what we know from the thing, and it's the difference from this object, which is that far from the center of the Earth, and from that far from the center of the Earth. So we have an object, the difference of the force, that's where we get from there. Okay, so for this next one, you'll see the top is the same, but now we're dividing by the I guess kind of the r values on the bottom. And so this is set up in the formula of the average rate of change. So I'll say that this is the average rate of change in, I'll say gravitational force, gravitational force. And I'll say for our units, it's going to be, now it's, this top thing is difference of forces, so those are newtons, and the bottom ones are meters. So in newtons per meter, newtons per meter, between 6,770,000 meters from the center of the Earth and 6,790,000 meters from the center of the Earth. Okay. So now, for the next one, it's going to be, we have our limited definition of a derivative. So it's going to be, instead of the average rate of change, it's going to be the instantaneous rate of change at 6,770,000. So the, see if I spell instantaneous right. Instantaneous, hope that's right. Rate of change of gravitational force in newtons per meter when an object is 6,770,000 meters from the center of the Earth. Okay, now for the last part, what does the solution to that represent? To f prime of r equals that represent? Well, the solution is going to be in r, so it's going to be a distance. And this is our derivative, so that's going to be the instantaneous rate of change. So it'll be the distance from the center of the Earth in this time, because it's a distance, it's in meters, where the instantaneous rate of change of the gravitational force, oh my goodness, such a long words, gravitational force is I'll put negative 0.000193 newtons per meter. And yeah, so you don't have to do any of the math here. You actually just have to explain what these things represent. So hopefully that saves you a little bit of time, but as you can see, this can be a bit wordy, but it's important to make sure you try to include as much as you can so they'll really fully understand that you're grasping what's going on here.
All right, so for problem 3a, we have to answer some questions based off of the graph of f of x. So if we come to this first question, it asks about the limit as x goes to 6 of the function. So we can see that on both sides, the limit approaches -2 when x equals 6. Now, f's derivative at 6 is a little bit trickier. So you see that the slope takes a sudden shift, a sudden move, and because it's so pointed like that, it doesn't exist at that point. The derivative does not exist, so we'll write d and e. Now, if we look at the limit as x approaches 6 from the right of a function at some x point, so it's kind of, we're looking for the slope as it's getting closer to 6 from the right, and so which that does have a limit, right? So that does have a slope, and we can see that it has a slope of 1. Okay, so now if we're looking at the limit as delta x goes to 0 of f of 8 plus delta x minus f of 8 over delta x. So this is, again, another way to write the derivative, right? So using the same thing, I mean, this is going to be kind of the same point, so it's going to have a limit value of 1. And now if we're looking at the limit as x goes to 2 from the right of f of x, that is also going to be approaching 1. And now if we look at the limit as x goes to -3 from the right, it looks like it's going to -infinity. And then if we look as x goes to negative infinity, the graph looks like it's closer and closer approaching negative 5. Now, if we're looking at the limit of the derivative as x goes to negative infinity, so what's happening to the slope of the function as x goes to negative infinity? Well, it's going to end up flattening out to kind of like a straight line almost, and we know that if there's a straight line, the slope of that line is going to be 0. And now, if we look at the limit as x goes to negative 4, that is going to be, if we look at these little points right here, because it will exist, that's going to give us 3. And now for 3b, it says identify a single value of x in the interval negative 10 to 10 at which f is continuous but not differentiable. Well, we kind of talked about that up here with this 0.6, where it's continuous. I mean, it has a limit from left and right that equal each other, and it has that same y value at that point. So, but it's not differentiable. And so that is going to be our answer. All right, so for problem 4, it wants us to use the limit definition of a derivative to show that the derivative of x minus x squared is equal to 1 minus 2x. All right, so if we remember, the limit definition of a derivative is the limit as h goes to 0 of f of x plus h minus f of x over h. So we have our function f of x is going to be x minus x squared, because that's what we're looking for the derivative of, right? So if we kind of model it after this limit definition of a derivative, we'll get the limit as h goes to 0 of, it's going to be x plus h minus, and then x plus h squared minus the whole function x minus x squared all over h. So then if we kind of expand some terms, that gives us the limit as h goes to 0 of x plus h minus x squared minus 2xh minus h squared, and then minus x plus x squared all over h. So we see we have some like terms that we can cancel out. We can cancel out these x squareds, and we can cancel out these x's. And so then we're just left with the limit as h goes to 0 of h minus 2xh minus h squared all over h. And so now that the numerator has these h's in common, we can factor one out. So that's going to be the limit as h goes to 0 of h times 1 minus 2x minus h all over h. And so now we can cancel those h's out. And so then we're just left with the limit as h goes to 0 of 1 minus 2x minus h. And if h goes to 0, that means that's going to go to 0, which gives us 1 minus 2x. All right, so number 5, it says without referring to a graph, determine whether the function f of x equals natural log of x minus cosine of x has at least one real 0 in the interval 1 to 3. All right, so if we think about the intermediate value theorem, or the IVT, we remember that if we have a function that's defined from a to b, and we're looking for a value, let's say f of c, and we know that f of a is less than or equal to c and f of b is greater than or equal to c, then there must be a c value which the f of c exists. And so in this case, if we're thinking about it in the context of this problem, we have our a starting point, and this function has to be continuous, right? So we have a, our starting point, which is 1, and our b, which is 3. So let's just look at our f of a and our f of b. So if we do f of a, It's going to be natural log of 1 minus cosine of 1, which is about negative 0.999. And then if we do our f of b, that's going to be f of 3, which is going to be natural log of 3 minus cosine of 3, which is 0.09998. So we see that f of b is positive, f of a is negative, and we're wanting to see if it has an x-intercept on the interval. So we're looking for an f of c is equal to 0, right? And so we say that because it's a continuous function from 1 to 3, and f of 1 is less than equal to f of c is less than or equal to f of 3, there must be a value c where f of c equals 0 by IVT. Alright, so we're given the graph function f of x, and for part A, we're supposed to determine a single numerical value for the constant b that makes the following inequality true. So the rate of change has to be greater than 0, so it has to be positive, but it has to be less than 1. So it has to be kind of a small rate of change, right? But still positive. So if we kind of take a look at the graph here, I'm going to look at point, let's see, f of 2 minus f of 1 over 2 minus 1. So if I write that out, it's going to be f of 2 minus f of 1, because 2 is 1 more than 1, right, over 1. So let's kind of look at the y values. So we have like 4.5 for 2, and then we have about 4.1. So that's going to be 4.5 minus 4 over 1, which is just 0.5, right? Which is within that bound that we're looking for. And so our b in this case is going to be 1. Now on part B, it says determine a single numerical value for the constant c that makes the following inequality true. And so if we notice this limit, this is like the limit definition of a derivative, right? So it's basically wanting where the derivative or the slope of the tangent line is equal to 0. And if we come back up to this region that we were looking at before, if we look at point 2, the slope of the tangent line there is going to be 0. And so our c in this case can equal 2.